No, stay right here.
Hi, we're at the 38th Annual Science Fair for Renfrew County here in Petawawa, Ontario at the Civic Centre. And we're here with Nathan Nguyen of Valor School in Petawawa. And he's going to tell us about the theory of everything. But first, let's find out a little bit more about Nathan. So Nathan, what grade are you in?
I'm in grade 7.
And is this the first time you've been at a science fair?
Yeah, like outside of my school, yes. This is the first time I've been to a science fair.
So grade 7, how old are you?
Oh, I'm 12 years old.
12 years old. Okay. Well, so have you been to a science camp in the summertime? How did you develop your interest at such an intricate level?
Well, my idol is kind of Stephen Hawking for his he overcome his amyotrophic lateral sclerosis. I found that kind of impressive. He's also one of the most brilliant minds in the world. And very recently he passed away, so I thought, I might as well do a bit of research on, string theory, theory of everything, which was one of his works, and reform it into my science fair project.
So, this is a tribute to your hero. And your hero being a scientist. That's refreshing in this day and age to hear that someone's hero is a scientist. So, your project is a theory of everything. Why don't you just take us through it from the very beginning?
Okay. So, sorry, this will be your typical science fair project, so sorry, no exploding volcanoes. But as you can see by the title, I will be talking to you, demonstrating, and modeling the singular unified theory of everything. Now, us as human beings yearn to have a complete understanding of the universe around us. And me being human, obviously, was intrigued how there could be one explanation to everything from matter, to energy, to the even problematic gravity. And although there is no direct experiment, remember that the theory of everything is in fact a theory, and cannot be proven unless you happen to have a hadron collider, which I highly doubt anybody here has. But anyways, I must also emphasize that the theory of everything I will be attempting to prove won't be quantum gravity or gravitons. I will be attempting to prove string theory. Now, first of all, what is string theory? String theory is a theoretical concept by quantum physicists to understand how matter, the force of our universe, and energy work in conjunction to create one cohesive universe, or to put it simply, the theory of everything. Now, to understand this, we must first understand the fundamental basics of our universe, and we can break this down into 3 sets of pre-existing knowledge. Quantum mechanics, Einstein's theory of general relativity, so take the word knowledge lightheartedly, and fundamental particles. Now, quantum mechanics are the study of tiny particles we know as atoms, but don't trust them because they make up everything. Ha 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 ha. Okay, anyways, bad jokes aside, they actually do make up everything, or at least matter. Inside the atom, we have something called a nucleus, which is right here.
Get a close-up of that. You keep on talking and he can...
It consists of protons and neutrons, and orbiting around them are electrons. There are different variations of atoms, depending on how many protons and electrons there are. Now, we also know that atoms, or at least different arrangements of atoms, can create different materials. Iron and water are a good example. Clearly one is a liquid and one is a durable solid, but the different arrangements of these atoms allow for these to be unique in their own way. Atoms also have what scientists call fundamental forces. This is the way atoms can interact with each other, if you will. So these interactions can result in forces such as electromagnetism and strong and weak nuclear reactions. Now, another key factor of our universe is gravity, and I'm going to be talking about it in Einstein's interpretation of it, so general relativity. So if we think about gravity, it's very important. If we didn't have gravity, we wouldn't be standing here right now, literally. So, to my surprise, gravity isn't actually a force of magnetism, but it is a force of space-time itself. Here, to show you what I mean. Do you mind holding these bottom 2 corners here? Thank you very much. Here we have space. Space is 3 dimensions, length, width, and height. The way Einstein interprets it is as this 2-dimensional fabric of reality. Do you mind closing up and top view? Thank you very much. This tennis ball here is our Earth. If I were to roll it across, you could see that it goes in a relatively straight line. this big heavy ball here will be our sun. If I place it in the middle, you can see that it creates a bit of a valley circling around the sun. Obviously, it's not a perfect interpretation. It's meant to simulate this, but this explains why gravitational forces are harder to get out of than into. Because what's easier, running downhill or uphill? Obviously running downhill. So, that is why gravitational forces are harder to get out of. Now to explain our orbit around the sun, we can take our Earth now, and we can see that it naturally wants to curve around the sun. See how it does that little loop? And this is why we orbit around the sun. The only reason we haven't fallen into its molten core yet is because we're sustained by our own gravitational field. Now, the problem with these two theories is that they don't always work in conjunction. So, mathematically, quantum mechanics and general relativity are often at odds with each other. If we knew that gravity could bend and manipulate these three dimensions, what other perceptible dimensions around us would there be for electromagnetism and strong and weak nuclear reactions to bend? There's no other visible dimensions for them to bend. Another problem with the two is that quantum mechanics works on the atomic scale. It works on something beyond our sight. And general relativity works on the universal scale. And obviously you can't count from 1 to 100 in a matter of 3 seconds. To put it simply, if our universe was a play, space-time would be the stage, and the actors and their performance would be the atoms and their interactions. But gravity states that this stage is moving, bending and curving in weird ways we did not know it could. And this creates a very messed up play, in our case, a messed up theory. Now, this is where we get into fundamental particles. So, do you remember the atoms I was talking about earlier? So, we took 2 protons, which were a part of the nucleus, and we put them in a particle accelerator, and we smashed them numerous times together until we got something even smaller. We found something called a fundamental particle, and these were so small that they had no substructure. But if these had no substructure, that means there's nothing smaller than them that could influence them
What are
to
they
make
called?
them different. Fundamental particles.
That's it?
Yep.
No name?
No name. There's different variations such as quarks and leptons, gauge bosons, and scalar bosons, each with their own unique properties. But, the general term for all of them is fundamental particles. Now, these fundamental particles behave differently, and they help us describe some of the forces of atoms. So, gluon, for example, could help explain forces such as strong nuclear reactions. Photons can help explain forces such as electromagnetism and light. And Z and W bosons could help us describe weak nuclear forces. Now, the problem with these is that we couldn't properly see them. We couldn't interpret them properly. So how do we see things? Photons, or light particles, would bounce off an object and go into our eyes as information. But these were so small that photons would just pass over them. So, how do we know they exist? What we did was, we shortened the wavelength, increasing its energy, and we sent it through so that there was less gaps for it to escape it. And once it touched, it transmitted back into a receiver. But the receiver didn't interpret the image properly because of the increased wavelengths. The increased energy disrupted the actual visibility of it, and it changed the way it looked. This is known as the Heisenberg uncertainty principle. So, instead of differentiating these fundamental particles characteristically, what we did was we just give it a rough estimated location on a 3-dimensional grid. They're not unique like us. I may have one feature that somebody else doesn't have, and they may have a feature that I don't have. But these are all the same. They're all perfectly identical. The only thing differentiating them was their location on a 3-dimensional grid, their estimated location. This is what helps us measure its mass, its charge, and its spin. Now, this is where we get into string theory. So, instead of interpreting them as the dots we initially thought it was to be, we interpreted it as strings. Now, here I have an electron. Obviously, the colors are all meant to be the same, but here is an electron. It's vibrating at a frequency that allows it to be an electron. It allows it to be unique, yet it's still the same as all the rest. And the only reason these frequencies allow for them to be different is because it's manipulating higher dimensional things, such as this. Imagine dimensions around us that we can't see properly. So if my thumb were a two-dimensional being, and we can clearly see this is a three-dimensional shape, but if I put my thumb on and I roll it across, the two-dimensional being would experience this track as if it were a two-dimensional layer, not a three-dimensional one. And the same thing can be applied to time. Although we experience time, we wouldn't experience it like a fourth-dimensional being would. Now, back to these strings. So here I created a standard model of a hydrogen atom. So these red ones here represents up quarks, which have a fractional charge of 2/3. This blue one right here is a down quark, which has a fractional charge of -1/3. And this green one is an electron. So right here, I have a proton, 2 ups and a down. Here I have a neutron, 1 up and 2 downs. And here I have an electron. Here we have a hydrogen atom. If I were to strum it, I can see that the vibration isn't very big. This vibration indicates gravity, and we can see that the gravity isn't very strong. Now if we were to add another one and vibrate it once more, we can see that the vibration gets bigger, and with one more, it gets even bigger. This explains why concepts like black holes, which are large amounts of mass confined to a very dense area, create strong gravitational pulls, because the more atoms we have, the more vibrations we have, which creates more gravity. And that for you is a very simplified form of string theory. And I hope I made it apparent that this is a theory worth finalizing. And if I have one hypothesis, it's that our generation of brilliant minds will be next to finalize it. Thank you for listening.
Thank you, Nathan.
No problem.
I wish you well in the finalist performance and the award ceremony, but regardless, everyone here participating is a winner already, getting into this and choosing science as a topic to spend several weekends on. And we certainly can look forward to the future with young, brilliant minds like this. Have you picked next year's science project?
Not yet, not quite yet.
How about the God particle? It builds on the bosons here. So we'll see next year what you've dreamt up. Take care.